Okay, so hello and welcome everyone to the sixth week for interactive live sessions on the for the course Computational Fluid Dynamics for Incompressible Flows. So the course is being offered by NPTEL, being instructed by Professor Amaresh Dalal from the Department of Mechanical Engineering at IIT Guwahati. My name is Debjit. I'm a PhD scholar at IIT Madras, and I'm the TA for this course. Like every week, we shall be solving some problems regarding this week's lectures. So, without any further ado, let us get started. So, here's question number one of today's session. So, this week has been all about finding out solutions numerically for hyperbolic equations. So in regards to that, you have to match the following. So the left column has three methods for solving hyperbolic equations. That is Euler FTCS, Euler BTCS, and Lax method. Now FTCS and BTCS, as you know, are abbreviations for uh, forward in time and central in space, and BTCS stands for backward in time and central in space. So you have to match them with the items on the right hand column, which is regarding the stability of those numerical schemes. So the three options there are unconditionally stable, conditionally stable, or unconditionally unstable. That is always unstable, cannot be stable uh, in any situation. So match them with each other, and once you have figured out the correct combination, you can pick options from the four available options given here. So it could be option A, A2B1 C3, or A3 B1 C2, or A1 B3 C2, or A3 B2 C1. So take your time, try to figure out the correct combination, and once you have done so, you can type it in the chat box or you can unmute and answer as well, however you feel comfortable. And throughout this session, if you have any questions whatsoever, please do not hesitate to ask them. Okay. All right. So let's have a look. I think we have a quick response, and that's in favor of option A, that is A2B1C3. Let's see what others have to say. Okay, so let's have a look at the solution. The solution is actually option B, that is A3B1C2. Let's see how we get there. Now, Euler FTCS scheme, option A. That is, so the model equation for hyperbolic equations looks something like this: dou phi dou t is equal to some minus c, that is the wave speed, because hyperbolic equations are basically wave equations, sort of. So now, how can we discretize this? So FTCS means we need to take forward in time. So n plus 1, n would be delta t, and here we will have central in space. So this is only first derivative, so it's just I plus 1 minus I minus 1. And since it's forward in space, so it's an implicit type of a scheme, so this would be n plus 1. And as we know, implicit schemes mostly are unconditionally stable. Sorry, unconditionally, so this one is unconditionally unstable, so A should be 3. Sorry, I did this wrong. So for FTCS it would be all the terms on the right hand side would be at the nth time level. So we are going from here to here, from the n to n plus 1th time level. So this is actually unconditionally unstable. Now Euler BTCS scheme, that is the backward in space, that's an implicit scheme. This one was explicit. Sorry, I spoke wrongly there. This is not an implicit but rather an explicit scheme. Similarly, this one would be n plus 1 minus n, and in this one we will have the terms on the right hand side which are unknown. So they belong to the n plus 1th time step. And this would be an implicit scheme which is unconditionally stable. So C should be, oh no, sorry. This would be conditionally stable. The condition here is that the uh, what is that? The Courant number, that is C delta x over delta t, that should be less than equal to 1. And C, which is Lax method, which is basically a modified form of the uh, FTCS scheme. Only so this is our FTCS scheme, like the first one which we wrote. Now here, instead of taking phi and 1, we will take an average of the at the nth level, but the average between the I plus 1 and the I minus nth location. Sorry, yeah, I plus 1 and I minus 1 at the both at the nth level and their average. And the right hand side would be same as follows. This method is unconditionally stable. Sorry, conditionally stable. So for this one, the Courant number has to be less than equal to 1, and BTCS scheme is unconditionally stable because it's an implicit scheme. Sorry, I misspoke quite a lot of times for this one. Please excuse me. So let's revise things once. So explicit scheme, the first one, the Euler FTCS, that is unconditionally unstable. That is never stable, so it's not useful. The BTCS scheme, the implicit scheme, that is unconditionally stable. This is always stable. That is a hallmark of all implicit schemes. So this is always stable. And the option C, the lax method, which is a modified form of the FTCS scheme, that is actually this has to be divided by delta. This one is conditionally stable, with the condition being that lambda has to be less than equal to 1, the Courant number. Okay, so I hope I cleared things up. I messed it up a little bit while going through it, but this is the correct solution. So A3, B1 and C2 should be the correct answer. Any questions on this? So the nature of stability is actually pretty similar to other parabolic equations as well, which we learned earlier, parabolic as well as elliptic. So explicit, only difference here is that the explicit scheme is unconditionally unstable. It's never stable. We have seen earlier that for parabolic equations, the explicit schemes are sometimes conditionally stable, given that the Courant number is less than 1, or not Courant number in that case, some other criterion given by the CFL criterion that has to be less than uh, some value. Okay, any questions on this? Okay. If not, we will keep moving on. We'll move on to question number 2 now. So this is now about three different methods. So for lax method, for CIR method, as well as midpoint leapfrog method, what is the condition for stability according to von Neumann stability analysis? So the von Neumann stability analysis, we will learn this in next week. So this will actually give all the uh, conditions for stability, or even predict methods which are unconditionally unstable or unconditionally stable, things like that. So for these methods, we can find out the condition for stability, and they happen to be the same for all three schemes. And I'll mention here the CIR method is known of named after three scientists: Courant, Isaacson, and Rees. So what is the criteria for them? Is it option A, lambda greater than equal to 0? Option B, lambda less than equal to 0? Option C, lambda greater than 1? Or option D, lambda less than equal to 1? Good. We have two quick responses in favor of option D. Let's see what others have to say. Okay, let's have a look at the solution. It's actually option D. This is something which we discussed earlier. So the Courant number, lambda, that is C into delta T over delta X. I think I uh, told this also incorrectly earlier once. So here also I'll write it down. Lambda would be C delta T over delta X. So this has to be less than equal to 1. So these methods, the specific methods, the lax method we already discussed in the previous slide, and the CIR method and the midpoint leapfrog method also we will discuss. So I'll just quickly hint. So CIR method is basically a combination of FTCS plus BTCS, and the midpoint leapfrog is basically CTCS, central in time as well as central in space. So, but for all of them, the common theme is that the Courant number has to be less than equal to 1. And there is some physical meaning attached to it. I would like to take some time to discuss that. So, basically, let's say there are these 2 points, and from one point to the next, there is information traveling. Information could be the temperature in heat transfer problems, it could be momentum in fluid mechanics problems, and so on. And so this speed of traveling of that disturbance is actually given by c, the wave speed in this case. So in time delta t, this disturbance actually propagates a distance c into delta t, the speed multiplied by time. It's pretty understandable, right? And the distance between these 2 points is delta x. So if c delta t is greater than x, then you can imagine that in one time step, the uh, disturbance would cross the next point and move over near the uh, further next one, and so the actual change in this point won't be resolved properly. So in order to capture it correctly, we have to go slowly. So the c delta t has to be less than equal to x, and that basically boils down to c delta t over x should be less than 1, or even equal to 1 works, but it should be sufficiently less than 1 in order to have properly stable solutions. Okay, so this is the physical meaning behind the Courant number being less than 1. Lambda here is the Courant number. Any questions on this? Was the explanation clear? The physical explanation why it should be so? Okay. All right. So moving on, we move on to question number 3 now. This is asking us match the following schemes with their appropriate conditions. So once again, these two schemes, FTFS and FTBS, work in certain situations where C could be either less than 0 or greater than 0. So you have to match the correct combinations or where it should be stable. Should, or rather, I would say that should not be unstable. That is what I mean by appropriate condition. So only two options are there. It could be either A2B1 or A1B2. And FTFS means forward in time, forward in space, and FTBS means forward in time, backward in space. So phi I would be there, whether you should take phi I plus 1 or phi I minus 1 for uh, modeling the dou phi dou x term is what is important here. What do you think? What should it be? Any guesses? So let's have a look at the solution. It's actually A1 B2. Yeah, so option B is actually correct as you said. So the underlying idea here is known as something as first order upwind scheme. So this word is important. I'll explain this later. So the thing is, we have our model equation like this: dou phi dou t equal to minus c dou phi dou x. Now, when C is positive, that is, when the flow is going from left to right, so if this is the ith point, we need to consider the point upwind of it. So downwind means downstream of that point, and upwind means upstream of that point. So if flow is coming from left to right, we need to take the point to the left of our point of interest, so which is I minus 1. So in this case, we need to take backward uh, in space. So if C is greater than 0, we need to take forward in time, backward in space. That's why FTBS should be for C greater than 0. And similarly, if C is less than 0, that is if the disturbance is traveling from right to left, we need to, once again, the idea here is that we need to consider the point upwind of it. So if you are calculating for I, we should consider the point at I plus 1. So basically this term, this dou phi dou x, we would discretize it as phi I minus phi I minus 1 in this case. and in this case we would have to consider I plus 1 minus phi. Sorry, not n minus 1, only n. Okay, so that's why A1 and B2 should be the correct answer. So why do we need to take the upwind scheme? So that the direction from which the disturbance is coming, we consider that direction. So the information is traveling from left to right. So in order to capture that, we need to consider the information at I minus 1 so that it propagates to I in this case. And similarly the one at I plus 1 so that it propagates back to the point I. So in order to capture that, we need to take the upwind scheme. And this is first order because this is, as you can see, is first order. There because we are considering only 2 points. So we can take multiple points in the upwind direction. So let's say for the case when C is positive, we could take multiple points upwind of I. That is I minus 1, I minus 2, I minus 3, and so on. So according to that, we would get a second order, third order, fourth order upwind scheme. One such scheme is the quick scheme. We will learn about this later. Okay. Any questions? So things are clear, right?
Sir, how to decide first order upwind or second order upwind?
Yes, so that actually depends on many factors. The first thing to keep in mind is that the uh, first order upwind scheme is easy to do. It is computationally quicker as well, so the solution would be much faster. But the disadvantage there is that some uh, uh, dissipation problems appear here. So this is also something that is discussed in one of the later lectures in this course. So by taking first order upwind scheme, we introduce some errors into our problem, which is similar to viscosity or diffusion in heat transfer problems. So that dissipation is there. So in order to eliminate that, higher order upwind schemes are used, but then the algorithm would become a little more complicated, and the solution time would also increase. So these are the pros and cons. Now we as CFD engineers have to, consider them and take a decision on which scheme to use when.
Right, sir.
Okay. Any other questions? So I'll just write this down. You brought up a very important point. So the first order upwind scheme, this has one disadvantage, is that it introduces some artificial dissipation into the problem. So there is natural dissipation, which is the diffusion, viscous diffusion in case of fluid flow, in which momentum is diffused. Similarly, in heat transfer problems, the thermal energy also gets diffused. So that the thermal diffusivity alpha we know. But in this case, even if there is no diffusion term in the original equation or the original problem, if there is no diffusion taking place, the mathematics of this problem introduces some artificial diffusion in this, and that is known as artificial dissipation. And that becomes a problem sometimes. Okay, so moving on, we'll move on to, and those things would be discussed later in later lectures as well. We will also bring them up in our questions and have a better discussion then. Okay, so now let's focus on question number 4, which is again a match the following type of question, in which you have to match the schemes with their order of accuracy. And if you quickly notice something, there are 4 options on the four items on the left column and three items on the right column. So it's not that the matching is unique. There could be multiple matching as well. So if you look at the options, it becomes clear. So if we take option A, for example, it's A2, B1, C3, D2. So the uh, second item on the right hand column, that is 2, is repeated twice. Similarly, in option B, 3 is repeated twice, and 2 is again repeated twice in C, and 2 is again repeated twice in D. Okay, so just try to find out what is the order of accuracy for each of the schemes. So the schemes are option A, CIR method, option B, lax method, option C, midpoint leapfrog method, and option D, lax Wendroff method. And the items on the right hand column are order of accuracy, first order in time, first order in space, option 2, first order in time, second order in space, and option 3, second order in time, second order in space. Let's look at some responses. Okay, we have one response in favor of option B. There is A1, B2, C3, and D3. One more response in favor of option B. Okay, let's see what others have to say. Okay, so let's take a look at the solution. It is option B, so well done, all those who selected option B. So let's go through each of them. The CIR method, which is a combination of FTCS plus BTCS. And I'll write down our model equation once again for clarity. So whether we do FTCS or BTCS, this is first order in space, and this is first order in time. So the CIR method is simply option 1, first order in both space and time. For the lax method, there we use a combination of, uh, or not combination of, we take the FTCS scheme and modify it a little bit, and that gives us the spatial accuracy of order 2. So the lax method is option 2. The midpoint leapfrog method, that is, remember, a CTCS scheme. I'll write this down. So for this one, we take central difference in time as well, 2 delta t. Sorry. So the CIR method is basically a combination of FTFS and FTBS. That's why this is first order always, because as we have seen earlier, that if we take central difference, then that becomes second order accurate. So the CTCS scheme, the lax method, or sorry, the midpoint leapfrog method, I'll write this as MPLF, midpoint leapfrog method, which is a CTCS scheme in which both central differences are taken. So for this one, it becomes 2 delta x, and we take a difference between I plus 1 and I minus 1, and these are at the time level n. So this derivative is second order accurate in time, and this one is second order accurate in space, right? And I'll explain this one as well. So the lax method is basically a modification of FTCS. So since it's CS, central in space, that's why it's second order accurate in space. That is the logic behind it. And Lax-Wendorf method, if we look at how it's derived, so basically all these terms, the dophi doti and dophi dox, not dophi dox, so dophi doti is expanded in its Taylor series form, and then the uh, time derivatives which appear, they are replaced by their space derivative counterparts, and what remains is again second order in time. The first truncated term, the higher order term, that is second order in time. If you want, I can discuss this method, but you can go back and take a look at the lecture how it's derived. So that gives us second order accuracy in both time and space. So D should also be 3. So the correct answer would be A1, B2, C3, D3. I hope I could explain this correctly. Any questions from anyone? I want you all to get a feel for predicting what would be the order of accuracy just by knowing what is the scheme being used. So forward in space, backward in space if we use, or even forward in time and backward in time, we simply get first order accurate only. But when things go to
Sir,
specific,
can you explain this Lax-Wendorf method? It's not very clear.
okay, so I'll do the derivation quickly, so that might make things clear. So the first term dofi doti is basically uh, written as this, right? Something like this. So if we expand this n plus 1 term in its Taylor series, so this becomes the phi I at n plus delta t into the first derivative plus the plus delta t square over 2 factorial, and this is also divided by 1 factorial into dou 2 t dou t dou, dou 2 phi dou t square plus higher order terms which are third order accurate. Okay, so this is the order of the next terms. Now dou phi dou t from this equation we know is minus c dou phi dou x. This is something that we replace this with. So we replace this with minus c dou phi dou x, and we can also take a time derivative of this entire equation, and that would give us this with some mathematical manipulations. Do you want me to do them, or is this clear?
It is clear, sir.
It is clear, right? So this term also gets replaced with c squared dou 2 phi dou x squared. Then we take this entire thing. So this we take this side and divide by delta t. That would give us, so I'm short of space here, so I'm writing here. Okay. So this would give us phi at n plus 1 and phi at n, the difference of them, and we divide them by delta t because that's what we want. And this would give us, so the first term which remains is this one, dou phi dou t, which is minus c dou phi dou x, which can again be broken up like this or in some other way. And similarly, this term remains, which is plus delta t by 2 okay, by 2 c squared dou 2 phi dou x squared plus c. We have divided both sides by delta t, so this term, the uh, delta t cube term, now becomes delta t squared, and higher order terms. So the error term over here, the truncation error, is actually order uh, delta t squared. That's why this is the answer. Is it clear?
Yes, sir.
Okay. And these terms, this dou phi dou x and dou 2 phi dou x squared, you know how to discretize them using central in space, right? So the dou phi dou x would simply be uh, phi I plus 1 minus phi I minus 1 divided by 2 delta x, and similarly this uh, dou 2 phi dou x squared would be I plus 1 minus 2i plus I minus 1 divided by delta x squared, and these are all second order in space, so second order in space as well. Okay. All right, so hoping things are clear, we will move on to question number 5 now, which is asking us what is the main advantage of the CIR method, which is the current Isaacson Rees method. Is it option A, high accuracy, option B, fast convergence, option C, unconditionally stable, or is it option D, independent of the direction of C? Which one would it be? The CIR method is again a combination of FTFS and FTBS schemes. Okay, so someone has said it should be option D. Someone says it's option B. Let's have a look at the solution. It's actually option D, independent of the direction of C. So the current Isaacson Rees method, that does a little bit of mathematical trickery, in which this term, the dou phi dou x term, is discretized as follows. So it basically is C dou phi dou x, right? So this is discretized as C plus mod C by 2 dou phi dou x. We will discretize this dou phi dou x in a different way. Let me just split this first. So, and C minus mod C by 2. You can see that if you do this summation, you will recover this left hand side that we began with. Now, the thing is, if C is positive, then this term remains and this term disappears. And if C is negative, then this term disappears and this term remains. So we now need to ensure that the dou phi dou x is taken in an upwind way in both different scenarios. So if C is positive and the first term disappears, or sorry, the first term remains, then this first dou phi dou x, this has to be discretized in an uh, uh, backward difference method. So that's why we would do this as backward difference we will take. Yeah, so upwind. And once again, for the other scenario where the when C is negative and the second term remains and the first term disappears, we need to discretize this dou phi dou x in a way that is upwind in that scenario. So we have to take a forward difference then. So this is how it becomes independent of the direction of C. You don't need to write different equations for depending on the value of C. This will automatically take care of the direction of C and give you the correct upwind scheme. So this mathematical trickery is used in the CIR method. That's how it becomes independent of the direction of C. Is it clear? How is it independent of C? Any questions? Anyone? Okay, good. So if not, we will move on to the sixth question now, which is asking us what is the stability criteria for solving Invisit-Burgers equation with the McCormack scheme. A few things to remember here. The Invisit-Burgers equation is basically a nonlinear equation, and nonlinear and hyperbolic as well. And the McCormack scheme is a predictor-corrector scheme, which is a multi-step method, a multi-step scheme method. Okay, so we have one quick response in favor of option D. Let's see what others have to say. Okay, one more in favor of option D. Let's have a look at the solution. It is actually option D. So there is really nothing to demonstrate here. So basically from von Neumann stability analysis, once again, if we perform that on the Invisit-Burgers equation, which looks something like this, dou u dou t plus u dou u dou x is equal to 0. Then for solving that, this should be the stability criteria if we are using the McCormack scheme. And in the McCormack scheme, what do? We go from the nth to the n plus 1th step with another step in between, that is n plus half. And while doing so, we can take, FTCS once and BTCS next, or the other way around as well. We can take BTCS first and FTCS again as well. So this is a combination of implicit and explicit scheme as well. Okay. Any questions? All right. So there are no questions. We'll move on quickly to question 7. Which of these is a multi-step method? Okay, I already leaked the answer to this one. Is it option A, midpoint leapfrog method? Is it option B, CIR method? Is it option C, Lax-Wendroff method? Or is it option D, McCormack method? Okay, so
Can you
yeah,
McCormack method
sorry, your
in
voice.
short?
Okay, yeah. McCormack method,
So
yes.
shortly, can you explain McCormack?
Yes, sure. Okay, so let's have a look at the solution. It is McCormack method, no surprises there. So what we do in McCormack method is that, as I discussed earlier, so from n to n plus 1, we do not go directly, we take n plus half step, and we use FTCS and BTCS in between. So what do we do? So let's go back to the original model equation. So dou phi dou t is equal to minus C dou phi dou x in the first step. So if the first step is FTCS, then we find out a provisional value of phi star, which I'm writing here. So this is corresponding to the n plus 1th step, but we are not explicitly writing it as so. Delta t equal to c, and there is nothing different here. So FTCS 2 delta x I plus 1 minus I minus 1, and these are all at the nth step. These are all known. From here I can find out what the phi star is. Now this is known as the predictor step. Then there is a corrector step next, which corrects this value of phi star. So there basically we take phi n minus, sorry, uh, phi n plus 1 minus phi star by delta t, and this should be equal to, and here we use the BTCS scheme. So this would be have to be at the n plus 1th level. Now we can do the opposite as well. We can take the backward in time step for the or backward in time method for the first step and forward in time for the second step as well. Okay. So go back to the lectures and look at it in more detail. I might be making some mistakes here as well, but this is how the overall McCormack method looks like. Okay. All right. So moving on, we'll move on to question number 8 now, which is asking us lax method is a modification of which discretization scheme? Is it FTCS, FTFS, FTBS, or BTCS? Given you know the meaning of all of these abbreviations, we have been using them for a while now, and you should get familiar with them as well. Lax method is a modification of which discretization scheme? Okay, we have a few quick responses in favor of option A, that is a FTCS scheme. Let's have a look at the solution. It's actually option A, FTCS. So we discussed this in one of the previous slides as well, but I will show this again. So basically forward in time. So this is how the first term gets discretized, and central in space. So this is how, sorry, I plus 1 n minus I minus 1 n. This is the FTCS scheme unmodified. Now in lax method, what we do is, now the disadvantage of this is we saw that this was unconditionally unstable. So it's useless. In order to make it useful, lax method was proposed, in which instead of using phi n, we use an average of uh, phi I plus 1n and phi I minus 1n. So this becomes, yeah, sorry, I wasn't able to hear you. Yes, are you trying to say something? Your voice is not audible.
Is required for FTCS.
What condition is required for FTCS?
Acha.
There's actually no condition for hyperbolic equations discretized in FTCS method because it becomes unconditionally unstable. There are no conditions which uh, under which it's stable. Did I understand your question correctly, or are you asking something else?
Got it, sir. Got it.
Got it?
Got
Okay.
it.
Okay. Thank you. All right. So
Thank you, sir.
yeah. Okay. So moving on, we'll move on to question number 9 now, which is asking us that Crank-Nicholson as well as Euler's BTCS scheme can be easily solved by which method? So solution method. There are several solution methods which we discussed earlier. So it could be a Gauss-Jacobi method, or a Gauss-Seidel method, or a line successive over relaxation, also abbreviated as LSOR method, or a tri-diagonal matrix algorithm method, or it's also known as Thomas algorithm. So which one is it? Crank-Nicholson as well as Euler's BTCS scheme, they allow themselves to be easily solved by one of these methods. Which one is it? Sorry, I think I lost my connection in between and now I'm back. Okay, so we seem to have a few responses in favor of option D, that is TDM. Let's have a look at the solution. It is indeed TDM. So in both Crank-Nicholson as well as Euler's BTCS scheme, what happens is that these are both implicit schemes, implicit or semi-implicit. Crank-Nicholson is actually semi-implicit and BTCS is implicit scheme. So in that case, we take three unknowns in every equation and we need to solve them in a matrix form because we get multiple such unknowns. So the equations can be cast in a way that, beta 1, beta 2, beta 3, dot dot dot, beta n. Similarly, alpha 2, alpha 3, 0, alpha 4, and so on. These are all zeros here. Alpha n, and we have gamma 1, gamma 3, gamma 4, sorry, gamma 2, gamma 3, and so on up to gamma n minus 1. And again, all these are 0 above these diagonals. So we have a main diagonal of betas, and we have two super and sub diagonals of alphas and gammas, and this is multiplied by the unknown fees. So I'll just write it this way: at the n minus or the n plus 1th level, these are all unknown, and this is this is equal to basically a function of all the known fees. It could be the phi in itself or some combination of them. But basically those are known values. That's what I mean. So this is how these equations look like. And we saw that these form of equations in which the matrix coefficients are can be resolved into three diagonals, then a tri-diagonal matrix if it becomes, then the Thomas algorithm can quickly solve this. Okay, so that's why option D would be the correct answer. Any questions on this? Okay, so if there are no questions, we'll move on to last question of today's session. So it is asking us the speed of propagation of the disturbance in hyperbolic problems is what? Is blank. Is it zero? Is it finite? Or is it infinite? A, B, or C? Okay, someone says it should be finite. Let's hear what others have to say. Option B, finite. Yeah. So let's have a look at the solution. It's actually finite. So good. So basically, c is the speed of propagation of disturbance, and it is always finite in hyperbolic problems. In elliptic problems, the speed of propagation becomes infinite, because if I make some change in one of the boundary conditions or anything, that that is, so change in boundary condition is basically a disturbance which is introduced, and that disturbance is felt in the entire domain instantaneously in zero time. So some distance traveled by the disturbance divided by zero time basically gives you infinite speed. So in those cases, for elliptic, it's actually infinite. But for both parabolic as well as hyperbolic problems, the disturbances, they propagate in a finite speed. They propagate with a finite speed. So basically, what does it look like? So one of the classic examples is the propagation of a wave. So if a wave looks like this at time t equal to 0, then it would look like something like this at time t equal to delta t, and at some time t equal to 2 delta t it would move even further, and these distances traveled by, let's say, peak from peak, these would be c into delta t, c into delta t, like that. So the propagation of that disturbance has a finite speed. Okay, does that make things clear? Any questions, anyone? Because I am out of questions. My questions are over for today. Okay, so if there are nothing else, then thank you all for participating in this session today. You have all been very responsive and attentive, so good. And we will meet again next week, and we will discuss more problems together. Thank you. Good night.